Good morning. Now we are going to have our midterm on Thursday, so please be punctual in attending the Zoom session. You are assigned two separate Zoom sessions, so please note your the Zoom session that you are assigned to and attend that Zoom session punctually. Okay, you should attend the Zoom session at least 10 minutes before the exam start, because we have to examine your student ID. Please bring along your student ID when you enter the Zoom session, and also please be prepared with some paper and pen for writing the answers, and also you have to use a device, your mobile device or a webcam, to to show your working to us. The examination is fully invigilated, but you are, however, allowed to use your lecture notes and also the books in your examination. You can view them in using your in your computer and using your mouse, but you are not required. You are not allowed to type anything and using the touchpad during the examination. So that's they are not allowed. You are not allowed to communicate with any people outside by using the internet or searching information on the web. That's also not allowed. Okay, so please be prepared for the exam. And actually, Kim, Kiu Jing has already announced that in the blackboard that he's going to help you in preparing for the exam by having 2 extra exercise class. So please note the time and the Zoom sessions of the extra exercise class. And if you need it to prepare for your midterm exam, please go to that extra exercise class. Okay, Kim is he uses spare time to do this. He's not mandatory to do this. So please value his contribution towards your understanding of this course. So if you need to find somebody for help, please go to that exercise class. He and any of us, including me, are ready to help you for preparing the midterm exam. Okay. So you just send a message to us and that's okay. Okay. Now, in the previous lecture, we discussed about how to define the talk, right? And we define it using this expression. We define it using the work done. Okay. Now, if we consider a circular motion, for example, and we apply the force F in a certain direction, which is not necessarily perpendicular or parallel to the radius of the circle, but we can always resolve this force in a direction parallel to the radius and perpendicular to the radius. We call this component F parallel, that means parallel to the radius, and F perl, F that is perpendicular to the radius. So apparently you can see that in a small time interval, the work done by the force is the perpendicular component of the force multiplied by the small displacement, because the perpendicular component of force is actually in the same direction as this displacement. The parallel component doesn't do work, okay? But the delta S for the small segment, it can be always be written as, in terms of the angle, delta theta as R delta theta. So if I group F perl and R together, and I define this quantity to be the torque, then the work done by the force will then be the torque multiplied by the angle, the change in the angle. So that satisfies our requirement. We want to define the torque this way, right? This is how we define the torque. So if we write the torque, if we define the torque as F perl multiplied by R, this equation will be satisfied, and this fulfill our expectation that the work done can be given by this expression. And the unit of torque is Newton meter. Now there are actually 2 views about torque. Now in your high school study, you may find the torque or moment of force by multiplying the force with the perpendicular distance from the point of action, right? The perpendicular distance of the pivot from the point of actions multiplying by the force will give you the moment, right? Now, the two points of view are actually equivalent. What we have introduced is the first one. We resolve the force in the direction perpendicular to this radius r. Okay, so we have the F pearl multiplied by r, and we define it as torque. Now, but if you look at this diagram and define the angle phi as the angle between F and the radius r, then F pearl is just F sine phi, right? F pearl is just F sine phi. Okay, you just resolve the force component in the perpendicular direction, and you got F sine phi. So the torque is actually Fr sine phi. Now, but if you use your secondary school point of view, which is the force multiplied by the perpendicular distance. Now we denote the perpendicular distance by R pearl here. Now this is a line of action of the force. We actually extend the force backward. Okay, we extend the force backward so that it forms a line of action. And the distance, the perpendicular distance between the pivot point and this line of action is called the R pearl. Okay, so from this point of view, you can say the torque is the force multiplied by R pearl. But you can notice that there's a right angle triangle here, right? And this is R, and this angle phi is just the same as this angle. They're alternate angle. Okay, so if you write it as R pearl can be written as R sine phi. So you have R pearl replaced by R sine phi here, and you get the same result of Fr sine phi. Okay, so you just use the convenient way for you to figure out the answer. You can either resolve the force component, use the perpendicular component multiplied by the radius, or you can multiply the force by the perpendicular distance. They both give the same answer. Okay. Now for linear motion, we have Newton's second law in the usual form, and that is F equal to ma. Okay, but the m is a constant, so it can be inserted into the derivative of v. The acceleration is the derivative of v, and since m is a constant, it can be put inside the derivative, and we define the momentum as mv. So the Newton's second law will take the form like this, the force being equal to the rate of change of the momentum. Okay, and for rotational motion, we expect the same thing. Okay, we expect the force to be replaced by the torque, the mass to be replaced by the moment of inertia, and the linear acceleration to be replaced by the angular acceleration. Okay, so we always remember this diagram. Everything in the linear motion has its angular counterpart. Okay, so we sit for an analogy with the linear motion. We want the same equation to happen to be valid in the angular case. Okay. Now, but I can also write the alpha in terms of the omega dt. The angular acceleration is the rate of change of the angular velocity. So it's given by the omega dt. And if I put the I inside the derivative, if I assume the I to be constant and I put it inside the derivative, I will end up having a relationship that is very similar to the linear case. The torque being equal to the time derivative of the quantity I omega. And it is suggestive for us to define this quantity I omega as another quantity called similar to the momentum. And this is called angular momentum. Okay. It is a rotational counterpart of the linear momentum. And in this formulation, it is defined as the moment of inertia multiplied by the angular velocity. Okay. Now, but all this expectations are just our guesses at this moment, right? We haven't proved it. We just expect the similar formalism to come out for the rotational case, but we haven't proved it mathematically. And now we are going to do it mathematically to show you that this formalism actually is completely analogous to the linear case. And so we're going to define L to define the angular momentum in a more formal way. And we eventually will find that for rigid body, the angular momentum become I omega. Okay, so let us go forward to define the angular momentum first. And then we find eventually the angular momentum is I omega. And then we will prove the Newton's second law for rotation. Okay. Now, how do we define the angular momentum? We know that the linear momentum is mv, right? The linear momentum p is just mv. So how do we define the angular situation? Well, just like the torque. For the torque, you first resolve the force into its perpendicular component, and you multiply the perpendicular component of the force by the distance of that point of action from the pivot. Okay, that is how you define the torque. Now we do the same thing for the angular momentum. We first take the linear momentum mv, okay, and then we resolve the linear momentum in a direction perpendicular to the distance from the pivot, which call this component p pearl, and we just multiply p pearl by r, and we define it as an angular momentum. Okay, so if you like, you can write everything in terms of this angle phi. The p pearl is actually p sine phi, but p is mv. So eventually you get mvr sine phi. Okay, you get mvr sine phi. So this is how you define the angular momentum. Now remember, the pearl here, the subscript here means the component of the momentum perpendicular to the component of linear momentum perpendicular to the radius, perpendicular to the distance between the point and the pivot. Okay. Now, having defined the angular momentum for a single particle, we go forward to define it for a system of particles. Okay. We suppose a rigid body. A rigid body means the body cannot be deformed. It is rigid. And so I can consider the whole body to be rotating about a certain axis with an angular velocity omega. Okay, so every point in the body has the same angular frequency. Okay, and for a single particle, we have, for example, the particle I. This is a label that denotes the I particle. And for the particle I, the angular momentum is the linear momentum multiplied by the perpendicular distance. Okay, so we have mvi multiplied by ri pearl. Okay, so this is the angular momentum for a single particle. Now here, we don't have to worry about the angle phi, because we know that for a rigid body rotation, the velocity vector or the momentum vector are actually perpendicular to the position vector. So the angle phi is just 1. The angle phi is just 90 degrees, and sine phi is just 1. So we don't have to consider this sine phi. It is only 1. Okay. So we simply multiply the linear momentum by the distance to get the angular momentum. So it's mv multiplied by r pearl. Okay. And of course, this is for a single particle. So we form a summation of all the particle to get the total angular momentum. Okay, here you can see for every particle labeled I or labeled J, they always have the velocity vector perpendicular to the position vector. Okay, so the angular momentum is simply mvr. Okay, now we then write the vi in terms of omega. V is equal to r omega by circular motion, right? So I have vi equal to ri pearl omega. Okay, and of course the pearl now stands for the perpendicular distance. Okay, and so I can make this 2r together, and that become ri pearl square multiplied by mi, and I form a summation of all this. Okay, and after forming a summation, I multiply by omega. Omega is a constant. It's the same for all particles, so that it can be taken out of the summation. So I now form a summation of mi pearl squares, and then I multiply by omega. Okay, but this summation is exactly the moment of inertia. This is how we define the moment of inertia of a body, right? So that means the angular momentum for rigid body can be written as the moment of inertia I multiplied by the angular speed, by the angular velocity. Okay, so that fulfill our expectation. L is in fact I omega. Okay, so this is what what we guess. Okay, and this is true. Now here we are going to proceed a step forward to prove Newton's second law in a rotational form. Okay, and we are going to do so by consideration of the energy. We use the work energy theorem again. Remember when we talk about the work energy theorem, we say if you input the work into the system, its energy will change, right? And we can imagine now the work done by the force is now going to turn the body and increase its energy of rotation. So we think this way, and we imagine that now we apply a force or a torque to turn the body. And the work done by the torque is equal to the change in kinetic energy of the rotation. Okay, so this is another version of the work energy theorem. In the linear case, we imagine the force to do work, and that becomes a change in kinetic energy. Now we have the rotational case. We imagine the torque to do work, and the work done now become the rotational kinetic energy of the system. But we know how to write both of this, right? We know how to write the W for rotation, and that's given by tau, the torque, multiplied by the angle, the theta. And for the kinetic energy of the rotation, we know this expression. It's just half I omega squared. We introduced the expression at the beginning of this chapter, right? So both expressions we know how to write out. Okay, so let's see if we apply the work energy theorem, what will follows. Now we differentiate this the half I omega squared, and that amounts to differentiate the omega squared. Differentiate the omega squared will be 2 omega d omega, right? But the 2 cancel with this 1/2, right? So we have this equation, tau d theta equal to I omega d omega. If I now divide both sides with dt, okay, so that the left-hand side will have a term with a factor of d theta dt. But that is of course the omega, the angular velocity, right? D theta dt is omega. On the right-hand side, again, I divided by dt, but I have the omega dt now, which is the angular velocity, angular acceleration, sorry. So the omega dt is the angular acceleration alpha, okay? Now I can see that the one of the omega cancel on both sides. So now the left-hand side become tau, the torque, and the right-hand side become I multiplied by the angular acceleration omega. Okay, so we have Newton's second law of rotation. Okay, we have proved it. That is, the angular acceleration of the body is proportional to the net torque acting on it, and is inversely proportional to the moment of inertia of the body about the rotation axis. Okay. Now, having proved the Newton's second law in the rotation form, we have more ground, we have more basis to interpret the moment of inertia as the inertia of rotation. Okay, so it just plays a similar role as a mass in a linear motion. Okay, it is it reflects how reluctant the body is to resist this motion. Okay, so if you have a larger moment of inertia, then you have a larger inertia. You are more reluctant to change your rotational state. That is the meaning of the moment of inertia. Okay. Now, so it plays the similar role. The moment of inertia plays a similar role as a mass in a linear motion. But there's an important difference that I want you to remember. The moment of inertia depends on the distribution of mass instead of the mass itself. Because it's the summation of the mass multiplied by the square of the perpendicular distance of those particles, right? So it depends on how the particles are distributed about the symmetry, about the rotation axis. If all the particle lines are lying far away from the rotation axis, then you will have a large moment of inertia. It does not only depends on the mass, but it depends on the mass multiplied by the square of the distance in this in a certain summation way. So it depends on the distribution of mass and also the axis at which you rotate the body. Okay, that is important to remember. Now, if you forgot the moment of inertia, I suggest you to have a feeling of it when you're at home. You can actually very easily to have a feeling of moment of inertia just by using a rod like this. Now, if I hold the rod at the middle and I rotate it like this, there's a certain inertia for me, right? It somehow resists my rotational motion because I'm shaking it around. So I have to change its motion constantly, right? So that means the rod has an inertia to my change. So I feel the moment of inertia of the rod in this sense, right? And you will find that if you hold it in the middle, the inertia is not much. But if you hold the rod at the end and you rotate it with the same angular speed, then you will find it more difficult. You will find the rod to be much heavier if you rotate it this way. Why? Because if you remember, the moment of inertia of the rod about its center is 1/12 of ml squared, 1/12 of ml squared. While at the end, if you hold it at the end and rotate about this axis, the moment of inertia is 1/3 ml squared. So it's 4 times as large. If you hold it at the end, the moment of inertia is 4 times as large as if the moment of inertia at the you hold it at the center. So that's why it's become more difficult to rotate it like this. You will feel much more heavier. So if you forgot the moment inertia, the meaning, you just try to do it at home, then you'll feel it. Okay. Now, having derived the Newton's second law in rotational form, I am tempted to go a little one step further. I write alpha in terms of d omega dt, and I put the I inside the time derivative. And then, since I have I omega be equal to L, that is our definition of the angular momentum. So I can write the Newton's second law in a form in terms of the angular momentum, and that is tau equal to dl dt. Okay, and L is defined by I omega. Okay, so we got everything essentially. But I actually is cheating you. Why? Because we have actually two forms of Newton's second law of rotation. The first form is in terms of I and alpha. The torque equal to I and alpha. The second torque, in the second form, the torque is equal to the time derivative of the angular momentum, which is I omega. Now, but there's an important difference between the two. In deriving this form of Newton's second law, we have assumed that the I is a constant, right? The I doesn't change when the body rotates. And that is only true for a rigid body. For a rigid body that cannot be deformed, the I remains a constant during the rotation. But that is not true if the body can be deformed. What body can be deformed? If the body is not rigid, then it can be deformed easily. Okay. For example, for a skater, when the skater rotates, you can see the skater may contract her arms, retract her legs, so that he becomes spinning faster and faster. Right. That is what commonly you seen in the skating competition. The skater simply contract her arms and retract her legs, and then she is spinning faster and faster in a nice way. Okay. So in that case, the moment of inertia is not a constant, and you cannot simply derive. You actually cannot simply derive the Newton's second law in terms of angular momentum just by putting I into the derivative, because the I is not constant. So this step is not valid. Right? This step is actually not valid for a non-rigid body. However, I will assure you that even though the I is not constant, this relationship, tau be equal to the rate of change of I omega, will still hold. Now, this is an assertion only. I haven't proved it, but it happens that to be so. I will amend the proof at the end of this chapter, but I don't want to use complicated mathematics to confuse you at this moment. So I just want you to accept this fact. The fact is, even though if the body is not a rigid body and I will change with time, this form of Newton's second law, tau equal to dL dt will still hold. So the time derivative now can act on both the I and the omega. So the I can also be changing. And this form of the angular Newton's second law of rotation is the most general form, which allows you to change the I. Okay. Now, so we will go back to this point at the end of the chapter, but at this moment, you just believe that the I can be changed. Okay. Now then, we discuss about a kind of rolling condition, which is known as rolling without slipping. Now, I think that it may be easier for me to show you what is called rolling without skipping with a simple model. Let me stop the sharing first. Now you see, now I have a disc, right? This is a wooden disc. Now I label 2 points here on the rim of the disc. And what I mean by rolling without slipping is the following. Now the book here, and now I roll this cylinder on the book. Now, when I roll, there's a relative sliding motion between the book and the surface of the cylinder. That is slipping. Now here we have the slipping. Okay, we have the slipping. So if you have a slipping, I cannot guarantee that the distance you move forward to be equal to the arc length between these 2 points, right? But if I do not have slipping, imagine that the friction between the book and the cylinder is large, so that when the cylinder rolls forwards, it's always attached to the surface of the book. And that is a pure rolling. Okay, I have a little bit of slipping at the end, but imagine now I am doing it very well. So it does not slip. It does not have a relative sliding motion. And that's called pure rolling. Now, if the rolling is pure rolling, then it is very apparent that the arc length between these 2 points, okay, here we have an arc length here. The arc length between these 2 points will be exactly equal to the distance moved forward by the cylinder when the cylinder rotates from this point to this point. Okay, when the cylinder rotates from this point touching the ground to this point touching the ground, the distance that is moved forward by the cylinder will be exactly equal to this arc length, right? So that is called the pure rolling. Okay. So here we have like this. Okay. Imagine now the cylinder roll forward by a certain angle, which we call delta theta. So initially the point A is touching the table, and after a while, after rotating this angle, the point B is now touching the table. Okay, so the angle turned through is delta theta. In the corresponding arc length between A and B will be given by the radius of the cylinder multiplied by delta theta. So delta S is R delta theta. If I divide this equation on both sides by the delta T, the equation becomes ds dt equal to R d theta dt. Now ds dt is what? ds dt is the distance, because it's a pure rolling, right? So the arc length is actually equal to the distance moved forward by the cylinder. So the SDT I can write as V with a big V, not a small v. The big V means what? The big V means the distance moved forward by the center of the cylinder. Okay, it's not the distance that the velocity move forward by the center of the cylinder. It is actually the center of mass velocity of the cylinder. So it is equal to the radius of the cylinder multiplied by its angular velocity. Okay, so in this relationship, I relate the translational motion of the cylinder with its rotational motion. The translational motion is the velocity that the cylinder is moving forward. But when this motion is due to the pure rotation, then the translational velocity is related to the angular velocity by this simple relationship. Okay, do you understand the meaning of capital V? Okay. Now it actually looks very similar to the circular motion formula that we have learned. The small v being equal to r omega, right? But the v here has a different meaning. For circular motion, the v actually means the velocity of a particle going through the circular motion. Okay, it is the speed that the particle move around in the circle. But here, the capital V has a different meaning. It is a translational velocity that the cylinder move forward. Okay, so please understand that this big V is not the same as a small v for a circular motion. Okay. Now, having learned all this basic thing, we are now ready to handle a rather complicated problem of a yo-yo. Have you played a yo-yo? I think you already have maybe your brother or your father may have played a yo-yo. A yo-yo is like this. You have essentially a cylinder, a solid cylinder, and there's an axle. And in the axle, you have a rope. You have a rope current around it. So when you release the yo-yo, the yo-yo will fall down under gravity, and the string that curl around the axle will uncoil itself. So it's actually rolling down. Okay. Now, so here we have a rope attached to the axle of a yo-yo, and now I'm holding the rope, the string at the top. So when I release it, the yo-yo will descend under gravity, but it is still under the action of the rope. So the tension force is still there. But as a string uncoil, the yo-yo will descend. Okay, and that happens in a pure rolling motion. So we are going to describe this motion, the release of a yo-yo. Okay, and we assume that the moment of inertia of this yo-yo above the axis is I, and we also assume that the axis radius is capital R. So the moment of inertia of the whole yo-yo is I, and the radius of its axis is capital R. Okay. Now, to solve this problem, we actually need two forms of Newton's second law. Two forms. The first form is for the translational motion. That's F equal to ma. Now, but be careful. What I mean by F here is the net force acting on the system. By the system, I mean the yo-yo. And A here, because the yo-yo is not a single particle now, it's a rigid body, right? It's a body with a dimension. And now we are going to describe its rotation, right? So that means that A does not refer to the acceleration of a single particle, but it refers to the acceleration of the center of mass of that body. Okay, so we are actually applying Newton's second law for a system of particles instead of just for a single particle. And A refers to the center of mass acceleration. Okay, and of course, in this case, it refers to the center of the yo-yo. Okay, the acceleration of this is center. Now, so what is the net force? Of course, we have the tension, right? And we have the gravity, but the gravity is larger than tension, so the yo-yo descends. So that means mg minus t is the net force. and the net force will produce the acceleration according to Newton's second law. So mg minus t is ma. Okay, that is the translational equation. And we also have the rotational motion in this case. And we apply tau equal to I alpha. This is what we learned. We have just learned, right? For the rotation. But what forces produce the torque? We can see from this diagram that only the tension will produce a torque. The gravity force will not produce torque. Why? Because the gravity force act directly at the center of the disc of the yo-yo, right? So that it is distant from the center is 0. And now we are describing the rotation by the torque about its center, right? So if the gravity force is acting directly at the center, it means that it has 0 distance from the center. And so it does not produce any torque about the center. So I do not have to consider the torque produced by the gravity force because it's 0. Okay. The only torque that I need to consider is the torque due to the tension force. And the tension force acts at the distance r from the center. So the torque it produces is TR. Okay. So that is the only torque acting on the system. And Newton's second law for rotation says it is equal to I alpha. Okay. Now we have 2 equations, right? Already have 2 equations, but we have 3 variables. Why? The tension is a variable, is unknown, unknown variable. A is unknown. Alpha is also unknown. So we have 2 equations with 3 unknowns, and we cannot solve it. So how are we going to solve it? Well, we have another condition that we haven't applied yet, and that's the no-slip condition. The no-slip condition corresponds to this. Okay, when the body rotates, it attaches tightly to the ground, so it does not slip on the ground. And in this case, when the yo-yo uncoil itself, the string will uncoil. When yo descend, the string uncoil, but without slipping. So that means the rotational motion and the translational motion, they are just related, but in the same way. So we have V equal to R omega, okay? Where V is, of course, the center of mass velocity. Omega is the angular velocity. V is the translational velocity of the center of mass, okay? Now I can differentiate it once more. If I differentiate the V once more, it becomes a center of mass acceleration. So V becomes A. And if I differentiate omega once more, the omega dp becomes the angular acceleration alpha. So I have A equal to R alpha. Okay, but that exactly allows us to eliminate one of the variables in the above equation, right? Because we now have the relationship between A and alpha. So we can eliminate one of the variables and solve the equation. Now, so let's take a look at the second equation. The tension force is equal to I alpha divided by R. But now the alpha can be written in terms of A over capital R. So it becomes IA over capital R squared. We just eliminate the alpha. We just write the alpha in terms of A. Now we substitute this expression back to the first equation. We replace the T by IA over R squared. And so we have this. And of course, the next step is to solve for A. And we move this term to the right. And we extract phi of A. And then we put the thing as the denominator of the right-hand side. And so we got the A equal to G over 1 plus I over mR squared. And that's, of course, more than G. Because this quantity is G divided by 1 plus something. And that something is larger than 1. So the denominator is larger than 2. So it's larger than 1. This quantity is larger than 0. So the denominator is larger than 1. And G divided by number larger than 1 must be smaller than G. Okay. So that means the acceleration is smaller than G. It must be smaller than the free fall acceleration. But that's of course the case because you have the tension, right? The tension will actually reduce the acceleration of the body. Okay. If you want to find the angular acceleration, that's easy. You simply divide A by capital R, and that's okay. Okay. Now, because in this situation, the A and the alpha, they are constant. And so if you want to find V and omega or S and theta, you can simply apply the equation of uniform accelerated motion or rotation. Okay, because now the yo-yo start from rest, so you don't have the initial angular velocity or the linear velocity. And so you have this expression. Okay, you can simply apply them to find the velocity, angular velocity, or the linear displacement, angular displacement any time. Okay. Now we now have a slightly more complicated example. This example is about a snooker. You know that, have you played snooker? Snooker has become very popular about 10 or 20 years ago, but it's no longer so popular now. But at that time, we actually play a lot of snooker. And the snooker involved using a cube to strike the ball, right? So you strike the ball with a cube, and the ball is given with a certain initial velocity. Now, suppose I use a cube to strike the ball at along the line that passes through its center. So essentially, I do not induce any torque on the ball, okay? Because the torque relies on the distance of the line of action of the force with the center. If I strike at the middle, then it will not induce any torque. And so there's a pure translational motion at the beginning. Okay, so the ball is given an initial velocity, which I call V naught. Okay, but what will happen in the next? When the cube leaves the ball, then ball is propelled forward. The ball will experience a friction from the table. There's a frictional force that tends to oppose the linear motion, right? So the frictional force is on the opposite direction to the velocity. Now, but mind that the frictional force is now acting at the distance r from the center. So that means the frictional force will have a torque about the center, and it will cause an angular acceleration. It will cause the ball to rotate, to be rotating forward. So after a while, the ball will acquire angular velocity omega, and it rotating like this, okay? Rotating forward. Now, so in order to describe its motion, we also have to set up two equations. The first equation is for the translational motion. Now, after the cube has left the ball, the only external force acting on the ball is the friction. But the friction is opposite to the velocity, so its direction is negative. So in my definition, my symbol F is positive. So I put a minus sign here to remind me that the direction is in the opposite direction to the velocity. So I have minus F equal to ma. That is a translational motion equation. I also have to set up rotational motion equation. The torque due to the force, due to the frictional force, is F multiplied by the radius R of the circle of the snooker ball. And that's equal to the moment inertia I of the ball multiplied by the alpha, the angular acceleration. So for the first equation, you can see the frictional force decelerate the linear motion. So after a while, the velocity V naught will be decreased to velocity V because the frictional force is opposing the motion, right? But on the other hand, the frictional force produces a torque, and it will make the ball to rotate faster and faster, right? So it accelerates the rotation. So it's quite interesting. It will be moving slower. The ball will be moving slower, but it will rotate faster after a while. Okay, so that's an interesting thing. So let's see what will happen eventually. Now, so the velocity decrease, but the omega increase. So let's plot a graph of V or R omega versus T. So this graph shows the variation of V and R omega. Initially, the linear velocity is V naught, but it's decreasing. So at any time, the V is given by this curve. This is actually a straight line because the acceleration, we assume the frictional force to be constant. So the acceleration is also a constant. So that means it's linear degrees. Okay. How about omega? Omega increase. But in order to put them in the same figure, I have to make them the same dimension. So I multiply by R. So the quantity R omega is increasing also linearly until eventually they meet at a certain point. When they meet here, that means the V is equal to R omega. Now, what is this? This is exactly the pure rolling condition that we have discussed earlier. So when pure rolling occurs, there will not the frictional force will will disappear. The frictional force arises because there's a relative sliding motion between the two surfaces. But when there's only a pure rotation along a horizontal surface, the frictional force will not appear anymore. So when the frictional force ceases to exist, the V will become R omega, and theoretically, the ball will roll forward without slipping forever. Okay, it will rotate rolling forward forever. But of course, in a reality, there's no such ideal condition. Of course, there's a small so-called rolling friction. There's a small sliding between also between the surface, but it's quite small, and so eventually the ball will stop. Okay, but theoretically, within the gradual auto detail, the ball will roll forever with such a velocity and such an angular velocity. Okay. Now, I want you to complete this problem in your exercise class. The TA will guide you to how to do it. Okay, so don't worry about this, and eventually you will see just like a pure rolling, the pure rolling of the cylinder like this. So the rolling will last for a long time. Okay, it will be rolling forward for a last distance. So that's why rolling is hard to stop. If you start rolling, that's much harder for you to stop than a sliding motion. The sliding motion will stop very quickly, but for rolling, actually you can reach a large distance. Okay, it's because of the pure rolling condition actually eliminate most of the friction. Okay, so it allows the body to roll a large distance. Okay. So this is only for your interest. There are some trick in the snooker, playing snooker. I don't know if you have learned it. The one of the trick is to strike the white ball at the base instead of at the middle. Now that will what? That will, instead of only inducing the translational motion, you will also induce a rotational motion. And the rotational motion will be in the anti-clockwise direction because you are using a torque that rotate the body in this sense, right? And that is anti-clockwise rotation. Now, so when the white ball collides with the red ball, it transfers all the linear momentum to the red ball. Okay, so the red ball will move off with the same velocity as the white ball, and theoretically the white ball will come to a stop. If the collision is completely elastic, the red ball will go off with the same velocity as the right ball, and the white ball will stop. But now we have the rotation. When the white ball stops, it is still rotating, but in the backward direction. Okay, so the rotation of the white ball actually will induce have a frictional force on the ground, and the frictional force will accelerate the white ball backwards. So after hitting the red ball, the white ball will be rolling backward, and that's called a school shot. Okay, school shot is the way to control the white ball position after hitting a color ball. It allows the white ball to go back after hitting the color ball, so that it can be positioned at a more favorable position for hitting another ball. Okay, so that's the idea. Now, let me show you a video, 學學費, but unfortunately it is in Cantonese, so forgive me if you cannot understand all the thing, but I can still show you the essential features that is the different ways of strike the ball to control the motion of the whiteboard. Now let's see it.
為咗贏黃子恒，大家繼續練習啦。
嚇，嘉琪打完一下就走咗啦。
心穎係運動叻啲，但都係打唔入喎。
你睇人哋又打入啦，實力真係差太遠咧。
點算啊？
你班是非精投降馬啦！
佢好囂啊！而家
可以咁樣嘅黑心，雖然佢靚仔啫，我哋唔可以驚佢嘅。好，我哋有第二個教練啊嘛。係，有師傅。我哋嘅教練喺嗰度。
我喺度。
湯博士，
又係佢啊！
湯博士，運動環節喎，打桌球都關你事，其實你係咪暗戀我啫？
梗唔係啦，打桌球都有物理學噶嘛，你唔學物理點打桌球啊？
咁你教我啦，你咁
我哋教你嘅，我哋齊跟阿湯博士上一堂先啦。
嚟啦！湯博士 OK 啦。
湯博士，波就已經 set 好啦，咁究竟桌球有咩物理咧？
嗱，其實咧桌球不外乎都係將個白波撞個顏色波落個袋度啫。嗱，如果個白波係正撞落個顏色波度，如果白波係冇旋轉嘅話咧，咁根據呢個動量守恒定律同埋能量守恒定律咧，個白波撞完個紅波之後咧，就會停咗喺度唔喐噶啦。個紅波咧就會好似白波之前個速度咁樣走落個袋度啦。
哦，哎呀，但係我唔係好明啊。不如你出去示範一次，俾我睇睇啊。好。
嗱，其實咧，子恒頭先打嘅咧就係喺個白波嘅中間，呢一個幾乎咧係一個完全嘅彈性動作。
It's almost an elastic collision.
將佢所有嘅能量咧傳遞晒俾個紅波。
So without any rotation,
而個紅波咧
all the energy will be transferred to the red ball.
向個袋邊走啦。
So there's a stun shot.
不如你試下今次打個白波嘅上邊，睇下發生咩事。
Now, Ziheng is now hitting the top of the white ball so that to induce a rotation. So the white ball will roll forward after the strike, after the collision.
仲向前流動嘅喎。嗱，咁其實咧白波嘅運動咧有兩部分嘅，一部分咧就係向前直線嘅運動，另一部分咧就係當你支 Q 打到白波嘅上邊嘅時候咧，其實佢係向前嘅旋轉運動㗎。咁當佢撞完個紅波之後咧，線性嘅運動嗰部分嘅能量俾紅波，但係因為佢之前咧仲有一個旋轉運動喺度啦，所以咧佢就會向前咁樣滾動啦。咁所以咪向前流咯。
聽完博士咁講，今次試下打白波
I strike the ball at
白波
base.
同紅波碰撞之後，先
So
會
after
停低。
strike, after the
因為白
collision,
波
it
有後
rotate
旋，
back.
佢同台面嘅摩擦力就會令佢向後滾動。
透過呢個原理，學識控制白波唔同嘅走向，咁打桌球就得心應手啦。
講完碰撞之後，聽講有種技術叫撞箍，連桌球小王子都話未必打到喎，究竟有幾難呢？
咦，咁 Sammy 得唔得咧？
哎呀，好難下喎！
即係點解？
嗱，你哋咧仲未明白呢個入射角等於反射角原理。好，等我攞塊鏡出嚟先。
你俾我哋照㗎？佢想我哋望下啲靚嘢。
唉，梗係唔係啦。其實咧係俾你練習咧點樣去對個入射角等於反射角。嗱，嘉琪啊，你而家試下咧打呢個白波，但係咧要對準鏡裏邊嗰個紅波嚟打喎，睇下打唔打中咯。
咦，咁樣又好似易啲喎。
你得㗎，我睇好你。
係。Yes， 湯博士，點解呢個方法會易咁多嘅？
嗱，其實咧呢塊鏡咧就反射咗張台嘅影像喎。當有塊鏡之後咧，成張台咧就好似反轉咗咁樣，形成咗一個影像啦。咁所以咧，當入射角等於反射角嘅時候咧，其實啊呢個紅波同埋呢個白波咧喺塊鏡裏邊咧就成一條直線。咁你對準個紅波反射嘅時候，咪打到咯。
You try？
俾得我實得啦，使乜事啫？唉。
Okay, so let's take a break.
How will professor taught you happens amuse yourself?
JC, okay?
It is okay.
Yeah, yes. Yeah, you should tell me immediately. Otherwise, yeah, otherwise that would be a very long time. Now in this example, we assume the cylinder to be a uniform one, and we write the moment inertia 1/2 mr². Okay. Now, but in general, the cylinder may not be uniform. You may have more mass distributed on, for example, on around the center than on the periphery of the cylinder. So the beta may not be 1/2. Okay, so let me make it general. Instead of writing 1/2 mr², we write that beta mr², where beta is a numerical constant more than 1. Okay, so along the inclined plane, the cylinder is acted by the force of gravity, which is vertically downward mg. And there's a component of force along the inclined plane, and that is mg sine theta. Okay, mg sine theta. So this component is along the plane, and you also have the frictional force to be directing upwards because the cylinder is sliding down. So the frictional force will be directing upward. So the net force will then be mg sine theta minus F. Okay. And the net force will be equal to the mass times acceleration. Okay. So that is the Newton's second law for translational motion. Okay. Now we can also have a similar equation for rotational motion, and that's tau equal to I omega. Again, the force of gravity does not work. Does not produce any torque because it's act directly at the center. So we do not we can ignore gravity, and we consider only the torque produced by the friction. The torque produced by the friction is Fr, and that's equal to I alpha. Okay. Okay. I is now beta mr², and alpha, if I consider a pure rolling without slipping, alpha is equal to A over R. That is only the pure rolling condition. Okay. And so if I put A over R to be alpha, then one of the R will cancel. And also I have another R cancel with the R on the other side of the equation. And so the frictional force will now become beta M8. Okay. So I can replace the friction in the linear equation by beta M8. And that allows me to solve for A. I move all the terms of the A on one side, and I found that A is actually equal to G sine theta 1 over 1 plus beta. Okay. Now I can, because the acceleration is now constant, so I can find the velocity of the cylinder after rolling a distance s. We can just use the equation for linear accelerate motion, the uniform accelerate motion in a linear case. So v squared is 2as. So v is square root 2as. And the a is given by g sine theta over 1 plus beta. The distance moved forward by the cylinder is along the inclined plane. So I can rewrite the distance in terms of the vertical height, h, that the cylinder has descended. Okay, so I can write s as h over sine theta, because h is s sine theta. So so the s can be written as h over sine theta. Okay, so this is s, and after canceling the theta, I find the v to be square root 2gh over 1 plus beta. Now you can see without the beta, if the beta is 0, that means rotational effect is not taken into account. If that is the case, then the velocity will simply be square root 2gh, which is just a conservation of energy you learn in high school. You release an object from a certain height, and after falling that height h, it acquires velocity equal to square root 2gh. That is the result you learn in high school for the case without no rotation. Okay. And also you can find the falling time again with the equation of uniform accelerated motion, S equal to half AT squared. Okay, and so you solve for T as square root 2S over A. The S is now given by H over sine theta, and A is given by G sine theta with 1 plus beta. And that means the T is given by this. Okay, now you can see an interesting thing. The time of the rolling along a certain distance S, it depends only on beta. It does not depend on the radius of the cylinder. It also does not depend on the mass of the cylinder. The only dependence on the property of the cylinder is the beta. Okay, and the beta depends on what? Depends on how the mass are distributed in the cylinder. For a uniform cylinder, beta is 1/2. Okay. Now, if we compare a solid with a hollow cylinder, you'll find a big difference in beta. For a solid cylinder, you know by doing integration that the moment of inertia is half mr squared. So the beta is 1/2. But if you have a hollow cylinder, what is the value of beta? If you have a hollow cylinder, then all the mass is distributed on, this is a hollow cylinder. If you have a hollow cylinder, then all the mass is distributed on the outer surface, which is at a distance r from the center, right? So if you have summation mr squared, all the r are the radius of the cylinder, which is capital R. So that means if you form a summation of all this miri square, that becomes the capital M multiplied by the radius of the cylinder square. So you have mr squared. So you have beta equal to 1, right? So that means what? That means for a solid cylinder, for a hollow cylinder, you have beta equal to 1. So if you substitute these two values into this equation, you can see which will roll faster. Which one will roll faster? Somebody answer me. The hollow one or the solid one? Which one has a larger time? Nobody knows? The hollow one, yeah, with the hollow one. Why? The hollow one with the I don't think so. Why? Because the hollow one will have a larger beta, which gives you a larger time. But this is a time for the cylinder to roll a certain distance. So a larger time for rolling means the cylinder rolls slower. Okay, so that means the solid cylinder will roll faster than the hollow cylinder. Okay, now you can think of it like this. This hollow cylinder has a larger moment inertia. So it becomes more difficult to rotate in a certain sense. Okay, so that means it rotates slower than the solid one. Now I give you a video to see. This is the experiment I did. I actually used this two things. Okay, one is hollow and one is solid. They have the same radius and the same mass. Now see, let's see what happened. I better share the screen with the video optimize. Now you see the solid one roll faster, very apparent, right? Okay, so that's the idea. Now you have another e-learning module here. You can review this, what I have taught with this e-learning module. And the teaching here will be a deeper to a different level than what I've just taught. So if you're interested to learn more, you can go to this e-learning module to review your understanding. We also have rotational kinetic energy. Now, when we talk about a body with both translational motion and rotational motion, just like, for example, a snooker ball, we will have the kinetic energy expression be given by the sum of the translational kinetic energy and the rotational kinetic energy. The translational kinetic energy is simply 1/2 multiplied by the mass multiplied by the velocity, the square of the velocity of the center of mass. So it's 1/2 m big V square, where big V is the velocity of the center of mass. Okay. And how about the rotational motion? Now, for the rotational motion, the energy, the moment inertia must be expressed as the moment inertia about the center of mass. So I write ICM here. Okay. And the kinetic energy that associated with the rotation is 1/2 ICM omega square, where omega is the angular velocity about the center of mass. Okay. So we count everything based on the center of mass. The center of mass translational velocity and the rotation moment of inertia about the center of mass and the rotation angular velocity about the center of mass. And if you count everything with respect to the center of mass, if you calculate everything with respect to the center of mass, the kinetic energy can be written as sum of two terms. It can nicely separate the translational motion kinetic energy and the rotational motion kinetic energy. They simply add up together. Okay, so that's a nice expression. That is a nice expression. But this expression will work only if the KE is calculated relative to the center of mass. If you calculate with respect to another point, this equation will not work. Now, I will have not shown you the general proof of this equation, but I will go back when we discuss when we have finished all the discussion in the main content, and I only will include the proof of this relationship and the extension. That means I will not test you in the final exam. In the final exam, you need only to memorize this sum of kinetic energy, the translational KE plus the rotational KE. Okay. Now let's solve the same problem of a cylinder rolling down inclined plane, but with the consideration of energy. Okay. Now this problem is not only for cylinder. It's also, you can also imagine a solid sphere rolling down, and for solid sphere you have beta equal to 2/5. Okay, so different rolling objects actually have different beta. Okay, but they share the same equation. Okay. Now, if you accept this relationship, you can just sum the translational kinetic energy to the rotational KE to get the total kinetic energy. And since we have pure rolling, we don't consider any slipping. So that means the angular velocity omega can be written as capital V over R. So now we have V squared over R squared. Okay. And so the I is beta mR squared, and the omega square is equal to capital V squared over R squared. So the R squared cancel. And now you can extract a factor of 1/2 mR squared out, and the expression become 1/2 multiplied by 1 plus beta mv squared. Okay. Now here we have the conservation of energy. We assume that the kinetic energy comes from the loss of potential energy. And the loss of potential energy is delta U. The gain in kinetic energy is delta K. The sum of the changes is equal to 0. And so delta K is equal to minus delta U. And that is our equation. Okay. This is the gain in kinetic energy. And the loss in potential energy is, of course, mgh, where h is the vertical distance of descent. Okay. The cylinder has, when it's rolled down, it actually has descent and vertical height of h. So its potential energy loss is mgh. And again, we get the same result. Okay, this is just the same result as before, right? Now there's a subtle question here that you may ask. Now I'm considering pure rolling. So, but there is a friction. There's a frictional force when on the inclined plane. But normally when there's a friction, we assume that mechanical energy is not conserved because there will be always work done by the friction. That is in fact the case when you deal with problem in your high school study, right? Whenever you have friction, you cannot apply the conservation of energy, right? But why in this case we can apply the conservation of energy even though there's a friction? Can somebody answer me? The answer is actually still there, okay, in this box. So can someone explain to me what was going on in this situation? No? Now, the answer is like this. Although there is a frictional force between the cylinder and the inclined plane, although there's a friction, but the friction does no work. But you may wonder why. Well, there's motion. But why do you say that the frictional force does no work? Now, the tricky thing is like this. Because we are dealing with a motion of a pure rolling. For motion of a pure rolling, every point that the cylinder surface will get in touch with every point on the inclined plane. And there's actually no relative sliding motion between the two surfaces. And if there's no sliding between the two surfaces, the frictional force does not work. The point in contact simply touch the surface at one point. It will not slide on the surface. Okay, so when you touch the surface one point, at another instant, that point will leave the surface without sliding over it. So that means the frictional force does not work, although it's there. Okay, so that means there's no work, no energy loss due to friction. I can assume that, and so I can apply the conservation of energy. Okay, does this make sense? Now, just a simple problem for you to do as a classwork. I have a small ball. The ball is so small that is small radius r can be neglected compared with the radius of this circular track. The circular track takes the shape of a quarter of a circle of radius capital R, and capital R is much larger than the radius small r of the sphere. And suppose now I release the sphere at the top of the track. So it rolls downwards along the track without slipping. And I would like to find the velocity of the sphere, a linear velocity of the sphere at the bottom, at the lowest point of the track. And we assume that the beta is 2/5 for uniform sphere. So can you do it? Okay, it's not difficult. You just remember the important things. The important thing is that, sorry. The important thing is that the KE is now equal to half mv squared and half I omega squared. So you have to know what is V, what is omega. And for pure rolling, you don't have, you actually have omega related to the linear speed of this ball, right? I see your response now. All right. Let's see if your answer is correct. You got 10 GR over 7. Let's see if the answer is correct. Okay. Anybody got another answer? Yeah. 10 GR over 7 square root. Yeah. I think you got the same answer, right? And let's see if it is the case. Now for pure rolling, you always have what? You always have the I written as mr square. But for pure rolling, we have omega written as v square for capital R square. So the R square here will always cancel, right? And you always will have the kinetic energy equal to what? Equal to half m 1 plus beta v square. Okay, so for pure rolling, actually this relationship always hold. The kinetic energy is instead of just given by half m v square, you have half m 1 plus beta v square. Okay, and if you equate the kinetic energy change with the potential energy loss, that would become half m v square 1 plus beta be equal to mg r. Now the height of descent is r. We assume the radius. Sorry, I made a mistake here. Sorry for that. I made a mistake here. Sorry for making this mistake, because now the radius of the sphere is more r. So the I is actually beta m r square. Okay, so this is m small r, but not big R. And for pure rolling, the angular velocity is capital V square over small r squared, but still the small r cancel. So this expression is correct, but this should be small r. Okay, and this is correct, and this is correct also, because now the vertical heights of the descent is capital R. If we neglect the heights, the little bit of radius of this sphere, the height is essentially mg big R. Okay. So we got V. The V is 2gr over 1 plus beta square root. Now the beta is 2 over 5, right? And so this will become 10gr over 7 square root. So you all got the same the correct answer. Congratulations. Okay. So this is the end of the first part. The first part of rotation. Now we consider a little bit today for the second part of rotation. And the second part of rotation is on equilibrium and also on the conservation of angular momentum. Okay. Now we consider extended body pivot above a certain point O. Okay. So we have a nail. Imagine you have a nail that pin the body towards a fixed wall, and the body is free to rotate about that pivot. Okay, can you imagine that? So now you have a rotation axis O that is pointing off page. That is your pivot point. That is your pin. Okay, so body is free to rotate about this axis O. Okay, now the center of mass is somewhere here in the body. Now let's consider how the weights of the body would produce a torque about the point O. Okay, we consider a general point mass in the body. I call this mass Mi. So its weight is Mig vertical downwards, and its perpendicular distance from the from the axis O is xi in this coordinate system. In this coordinate system, I assume this direction, the horizontal direction, to be the x direction. So so this point mass actually produce a moment of MIG about the axis. Okay. So the torque that is produced by the weights of this point mass is MIG multiplied by xi. The weight of the point mass multiplied by this perpendicular distance xi. And of course, we should form a summation because we consider the whole body. So the summation of all the point mass in the body over the quantity MIG xi will give me the total torque due to the weight of the body. But let me write like this. We form a summation of Mi and xi first, and then multiply by g. Because the g is constant, it can always be taken out of the summation. But by definition of the center of mass, summation Mi xi is equal to what? When I divide by capital M, it is equal to the center of mass position x, right? So that means this summation is equal to the mass times the center of mass position x. And so I have mgx, okay? So that means what? That means I can imagine all the mass to be concentrated at the center of mass position. And it behaves just like a point mass to produce a torque. Because the torque produced by a point mass here at the center of mass position is the mass mg, the weight mg, multiplied by the center of mass position x, which is exactly this expression, right? So we do not have to consider summation again and again next time. When we see a rigid body like this, and the weight is located at the center of mass, we directly can write down the torque produced by the weights. It is the mg multiplied by the perpendicular distance from the pilot point. Okay, and of course, by perpendicular distance, I refer to the position of the center of mass. Okay. And also there's, for the energy, it's also the same. If I consider a point mass Mi as a height Zi above a certain reference level for the potential energy, then I have the potential energy of this point mass as Mig Zi, right? And if I form a summation over the whole body, and that I will get the total potential energy. But again, I can rewrite the Mi Zi as capital M multiplied by the center of mass heights, the heights of the center of mass, Ez. Okay, so eventually I got the same relationship. I got the potential energy of the whole body as mg(Ez). So again, I can consider the whole thing as a point mass, and the energy is just the point mass, a point mass located exactly at the center of mass position. I just multiply the mass with g and also the heights of the center of mass above the reference level. Okay, so that's just nice things. So that means in many of the calculation, you can actually replace the complicated summation with the center of mass position. You imagine the point mass torque to be located at the weight to be at acting at exactly the center of mass position. And so it produces torque exactly at that position. And the energy is also associated with the height of that position. Okay, so that simplifies a lot of calculation. Now, when you consider a laminar like this, which is pinned about the axis O on the wall, so that the laminar can rotate freely, swing about the axis O. Okay. Now, suppose now the center of mass is at this position, which is not vertically below the axis, and so there's an angle. Okay, if you draw the center of mass with the axis, it makes an angle theta with a vertical, and so the center of mass will produce a torque about the axis O, and the torque is given by what? It's given by the weights of the body mg multiplied by the perpendicular distance, which is r sine theta. So mg r sine theta gives you the torque. Okay, the r sine theta is this distance, is the perpendicular distance of the center of mass from this line. Okay. Okay, so this is a torque, and the torque will always tend to decrease theta. If you release it, the torque will accelerate the object downwards, and that always tends to decrease the angle. Okay, if the body swing to another side, the torque will also decrease the angle, tends to decrease the angle. So after swinging maybe a few times, there will be frictional loss due to there will be loss in energy due to friction. The body will eventually settle with its center of mass position lying directly below the axis of rotation. Okay, and I find that this is a stable equilibrium position. When the center of mass is directly below the point of suspension, that will be the most stable configuration of this lamina, and that's a stable equilibrium. If you consider the lamina to be slightly displaced to either direction, you will immediately realize that the torque will always tend to restore the lamina back to this stable configuration. So that is a stable equilibrium. Okay. Now you can also examine, understand this by using the potential energy, because the potential energy is related to the height of the center of mass, right? Here, if you have the lamina slightly displaced, the center of mass potential energy will, the center of mass position will be raised. So you have higher potential energy. And when the center of mass position is exactly below the point of suspension, the center of mass position is the lowest. And so the body will also have the lowest potential energy. Okay, so that again explains why this position is a stable equilibrium. When we learn about the stable equilibrium, we learn about when the potential energy reach a minimum, the equilibrium will be stable, right? So that is exactly this case. At the lowest position of the center of mass, the potential energy is the lowest. So that is a stable point for the equilibrium. Okay. Now there's actually quite a lot of tricks using the center of mass position. For example, you can find the center of mass of a lamina by doing this. You hang the lamina at one point, at one axis, one point on its rim, and then its center of mass must be directly below this point of suspension. Okay, by this argument, right? Because it's a stable equilibrium, right? So if you draw a plumb line, if you connect a plumb line here, the center of mass must be along the plumb line. Okay, and if you do the same for the other 2 points on the lamina, for the other 2 points, you do the same, and there are 2 more lines result. The 3 lines must cross as a position of center of mass, and so that's how you find it, the position of the CM. Okay. This is also another trick. It looks unstable, but actually it is stable. Why? Because the fork is placed lower than the point of suspension. So the center of mass position is actually somewhere below the point of suspension. And so when the whole body is slightly disturbed, the center of mass position will be raised, and the torque it produces, the center of mass position will tend to restore the equilibrium. So the important thing is that when you suspend a body with a center of mass position below the point of suspension, then you can have a stable, very stable equilibrium. Okay. Now this is the bird I showed you earlier, right? It can be stably levitate above the nose, right? And in fact, the bird has the center of mass position directly, just directly below this point. Okay, it's not exactly at the nose, but at the position slightly below the nose. So again, you can imagine it's like a rigid body being hanged be directly below, with its center mass position hanging below the center mass, the hanging position, and that is a stable equilibrium. Okay. Now we can use this property for us to do the calculation. For example, if we have a rod, I finished the example before letting you go. If you have a rod suspended at one end, okay, and you release the rod at a certain angle, and let it falls down, okay. And for simplicity, here I assume the rod to be initially at an angle, making an angle favorable with the vertical. So I can consider this motion using the energy. Okay. Now I use this point at the reference position for the energy. Okay. And initially, the center of mass is at a distance. This is half of the length, alpha 2. And if this angle is theta, then the height of this center of mass below the point of suspension is L cosine theta over 2. Okay, L over 2 cosine theta. Now, when the rod falls down, and at the instant when the rod is along the vertical line, the point of center of mass will be exactly at the height of alpha 2 below the point of suspension. So the change, in the position of the center of mass, sorry, I should write the change in position, not the position. The change in the position of the center of mass is alpha 2 minus alpha 2 cosine theta. Okay, so the change in position of the center of mass, I should write here. I will amend it later. So the change in the position of the center of mass is alpha 2, which is the final height, minus the initial height, which is alpha 2 cosine theta. Okay, the final height is actually lower. Okay, so L over 2 is larger than alpha 2 cosine theta. So this is the change. If I multiply by mg, I have a minus sign. That's a change in potential energy. Okay. The kinetic energy change is half mi omega square, where omega is the angular velocity at the lowest position, as a vertical position. And for a rod that is hinged at one end, the moment of inertia is 1/3 ml square. Okay, so now I have 1/6 ml square omega square. Okay, and of course I equate the change in potential energy to the change in kinetic energy. I put absolute sign and equate that to, I got the omega. The omega is the angular velocity when the rod is vertical. Okay, so in terms of energy, I solve this problem. Okay. Now there's also other kinds of trick. For example, you can have Coca-Cola cans stably supported on table but tilted. If you pour 100 milliliter of water into the Coca-Cola can, you will find that the center of mass position of the water together with the can is directly above the slightly tilted base. So although this equilibrium is not quite stable, but as long as you have a finite area for the base, you can still achieve a certain equilibrium. And that equilibrium is actually quite interesting to look at. And also you can use a center of mass position to study the equilibrium position by stacking the book directly outward. Okay, so you can stack many books as long as for each book the position of center of mass is within the rim of the other book. This can be stable. Okay, this is another trick you want to pay. Now, then I will talk about the condition for equilibrium, but I prefer to stop here because this is rather complicated, so I need more time to explain. And so I stop here for my lecture.